For section 2.8, we're going to look at one-to-one functions, and then off of that idea, build the idea of an inverse. A one-to-one function, first of all, it is a function, so we know by definition that means it passes the vertical line test. But a one-to-one function also means that no two elements in the domain have the same image or the same element in the range. So an example of something that's not one-to-one would be if I had the point 2, 4 and the point 2, -4. Excuse me, let's try that again. That's not even a function. I meant to say -2, 4. There we go. So that is a function. I don't have any repeated x's, but since two different x numbers go to 4, this would not be a one-to-one function. It's easier to look at it graphically. A one-to-one function basically passes the horizontal line test. And this is, by the way, this IFF means if and only if. So a function is one-to-one if and only if no horizontal line intersects it more than once. And we're going to see this as we go through these examples. I'm going to show you the graphs. Once we know that a function is one-to-one, then we can build an inverse function. So its inverse, we use the symbol f -1. Basically, the inverse switches the x and y's, or switches the domain and range. Notice it says the function has domain A and range B. If I switch those, the inverse has domain B and range A. Basically, an inverse undoes whatever a function does, and we switch the x's and y's. So that's going to be the idea, to figure out the inverses of these functions on number 1. So they're already functions. They all say f of x equals. So that's identifying that they are functions. But are they one-to-one functions? We can do this algebraically, but I think it's easier to just think of the graph. 4x plus 1 is just a line starting up 1 with a slope of 4. I'm going to show you on some graphs on these ones. So the question is, does that pass the horizontal line test? And it does. No horizontal line would hit it more than once. So yes, it's one-to-one. And how do we find the inverse then? Well, f of x, think of that as your y. As I mentioned, an inverse basically flips the x's and y's. So algebraically, I'm going to do that. I'm going to call this x and this y. And now I'm just going to solve for the new y. So if I subtract 1, I've got x minus 1 equals 4y. If I divide by 4, I get x minus 1 over 4. That's what that new y would equal. I'm going to use functional notation and call that f inverse instead. So this is the inverse function, which is another line. There's the inverse in blue. Something I want you to notice, and this will come up on the other problems as well, a function and its inverse graphically are perfect reflections over the line y equals x. The line with a slope of 1, y equals x. Notice that the red and the blue perfectly mirror each other over that dotted line. That's always going to be true of a function and its inverse. For letter B, we have a square root function, 2x minus 5, and x has to be greater than or equal to 5/2, otherwise we'd have the square root of a negative. Well, square root functions, and again, this is why you study these so much in algebra, look something like this. That would be forever rising. It does pass the horizontal line test. So yes, it is one-to-one. So that means I can find an inverse function. So same logic. Think of f of x as your y. switch x and y. I'll deal with the restriction in just a second here. So I've got to get stuff away from y. So the first thing I'd have to do is square both sides. That's x squared equals 2y minus 5. It's a y. Next step will be to add 5 over. And the last step would be to divide by 2. So I'd have x squared plus 5 divided by 2. That's my inverse. Now here, I've got to be a little careful. And this is where a little bit of not just pure do the problem comes in, and I've got to think a little bit. That is a parabola. If I think about that, a parabola, my original function was the square root function, which looked like this. A parabola is going to look like that. Those are not going to be mirror images, the orange and the blue. We have to restrict ourselves on the parabola to basically cut off the parabola at the vertex. So I'm going to cut it off where I can only see part of the parabola. The way I do that is algebraically, I write x has to be greater than or equal to 0, because on this particular parabola, my vertex has an x coordinate of 0. That's a subtle point. I'm not going to mark off if you don't remember that, but I just want you to be aware of it because you will see it come up in this class, and you'll see it a bunch in calculus. So looking at my graph, notice that I have x squared plus 5 over here, but notice that I restricted my x. That's going to only give me half of a parabola. And I can see that those two graphs, again, are perfect reflections of one another over the line y equals x. For letter C, well, think about it graphically. This would be a parabola opening down, starting up 6. So if I ask myself, all right, is that 1-to-1? It does not pass the horizontal line test. A horizontal line would hit it more than once. So this one is not 1-to-1. So I can't find the inverse function because it's not a 1-to-1 function. Now, if you're saying, well, that's great if I can see the graph, but I'm not so great at graphing, I want you to see what would happen if I tried to solve this. You don't have to write this down, but if I switched my x's and y's and tried to get the new y by itself, so maybe let's say I add the y squared over. There's a couple ways I could do this. I subtract the x over. And now here's the hitch. If I take the square root, that would technically give me a plus or minus for the y. That tips me off that this is not 1-to-1. If it's 1-to-1, I should only be getting y equals a single function. I'm getting y equals 2 functions because of that plus or minus. So that tips me off that it's not 1-to-1. There is no inverse function. Now letter D takes that same exact function, but now it restricts itself on the domain. It says, all right, let's only look at this function for x is greater than or equal to 0. So looking back at my graph, I now restrict myself to x is greater than or equal to 0. Oops, I did less than or equal to. Let me change that. Now I did it. So this is kind of the math way of fudging the numbers, if you will. We know it wouldn't work, so we say, all right, let's only look at part of it. Let's not look at the whole parabola. We'll actually do this same idea when we get to some trig stuff in later units. So now I can. So now the same stuff I just did on the previous problem, I'm going to do again. So yes, now it is 1-to-1 because of the restriction. So now I can say, okay, let's think of that as y. Let's flip it. And again, I'm going to go through the same process I just did on the previous one. Oops. It needs to be a y. So I flipped my x and y. Again, you can go through this however you want. You'd end up with y squared equals 6 minus x. You'd square root. I don't need to worry about the plus or minus because since I restricted x to be greater than or equal to 0, that means the inverse is also going to only be the positive. Actually, instead of writing y, I'll write the functional notation. F inverse is root 6 minus x. And if I look at those two functions, they are perfect reflections over the line y equals x. So graphically, it seems to keep working. For letter E, 4 over x squared. You've done this in previous classes. You may not remember, but it's a rational function. This graph looks like that, which does not pass the horizontal line test. So this one's not one-to-one. So we're done with that one. Now letter F is a tricky one. A little star on this or something. This one's a little nasty. If I look at the graph of it, it is one-to-one. Remember those asymptotes that happen? This has a vertical asymptote and a horizontal asymptote, but there's no single line that would hit it twice. No single horizontal line, excuse me. So it is one-to-one. So that does mean I can find an inverse. Now, following the same logic as I've been doing, call it y, switch your x and y. Now it's x equals y over 2y minus 3. Now, the issue with this problem is that y is in two different spots. I can get it to one spot, but it's going to take a little bit of work. First thing I'm going to do is multiply the 2y minus 3 over here. If I do that, that's going to be 2xy minus 3x equals y. All right, notice that I've got y still in two spots. Well, I'm at least going to group it together. So here's what I'm going to do. I'm going to subtract this y over so it's on the same side. That's going to be 2xy minus y. The 3x I'm going to add to the other side because it doesn't have a y in it. I want to get it away. So still y is in two spots, but now it's grouped together on the same side. I can factor the y out. This will be y times the quantity, 2x minus 1 equals 3x. So if my variable is in more than one place, get it grouped together on one side and factor it out. So at this point, all I have to do to get y by itself would be to divide the 2x minus 1 over to the other side. So what I'd end up with is my inverse is 3x divided by 2x minus 1. So a little trickier, took a few more steps, but we still got there. Just to show you, this is going to start to look a little convoluted, but here's the function we just found. Notice that those two, even though there's a lot going on here, they are reflections. So if you focus on like the top halves of them here, the gray and the kind of brownish are perfect reflections. Same thing down here. So it did work. For number 2, this will be the quickest and easiest question of the entire semester. Given f is a one-to-one function, okay? We know it's one-to-one. If f of 6 is -3, then what is f inverse of -3? Remember that a function and its inverse just flip the x's and y's. So basically, if 6 outputs to -3, then on the inverse, -3 must output to 6. I'm just flipping the x and y. This was x, this was y, they just flipped. Easiest question, nobody should get that one wrong. On number 3, I'm going to build off of that concept. I've got a function, but then I want to know a value based off of the inverse. Well, let's think about this. If 5 is the input of the inverse function, then 5 must be the output of the original. So 5 must actually be the output of the original function. So I'm going to replace f of x with 5. So basically it's saying if 5 goes to something in the inverse, that something, because remember they flip the x's and y's, must be the x in the original. So I'm setting the output to 5. So 5 equals x squared plus 4x. Looks like a quadratic to solve. I'm going to subtract over 5. This does factor. It'll factor into x plus 5, x minus 1. Now that's going to give me two x values, -5 and 1. So what's my answer? Well, it said I only want that function for values bigger than or equal to -2. So -5 is cut off. Basically, I had a parabola here that, again, I had to slice off one of the arms of the parabola so that it became a 1-to-1 function. So the answer that's bigger than -2 is 1. So in the inverse, if I input a 5, it should spit out a 1, because I just figured out that inputting a 1 into the original spits out a 5. All right, that'll do it for the first video of this.